That water went down my lungs. I'm better now. All right. So let me go ahead and let's dive in here. All right. So let me get my spacer set up here and my pen back here. Okay. All right. Here we go. Yes, Zach. So let me write that down. I'm going to post up the slides as well. I have them. They're instructor only slides, but I don't care. I'll get those out. PowerPoints post. Got it. Written down. All right. All right. So first we're going to talk about OSI model and encapsulation. You can see that this is about a 28. Well, you can't see that, but this is about 28 slides. So it's not that big of a chapter. So we'll probably be able to blow through this pretty quickly here. So anybody has questions, go ahead and throw them in there, and I'll answer as we can. You have comments and quips are fine too, but let me go ahead and move along, and I'll answer them as I see them and have time. So we're talking about networking, right? So thousands of years of communication still evolving, signals, symbols, language, sender to receiver. That's communications, all right? So that's what that's all about. So there used to be many different communications protocols, and a protocol, I guess you should say, is a protocol is like a set instructions on how to make this communication happen, right? So common elements were identified, and they called this the OSI model, or the Open Systems Interconnect model. And that model included many different communications protocols. You see a lot of them on your left right here. Some of the big ones that you're going to be talking about in this class are, well, it didn't want to let me do that. Oh, I know why, because I'm not on. Am I on? Oh, hang on. Yep, I don't have editing enabled. That's why. And then I need to go ahead and put my pen on. Pen. All right. So we're going to talk a lot about TCP/IP. Maybe Ethernet over here. We'll have a lot of communications on right here. Why is this pen not working? Huh. What did you do? There we go. I don't know. It's flipping out of me. I ain't going to use the pen. Going back to the mouse. Yeah, so we can go Ethernet. When we talk about Windows stuff, we'll talk about some NetBIOS. A lot of these things are still around, but a lot of them really are, a good fair amount of them have been deprecated at this point. So Open Systems Interconnect model is OSI. So we're talking about the OSI model versus the TCP/IP model. The TCP/IP model is a model that came out later on, and it's a shortened model, but it aligns up with the OSI model. So where does TCP/IP fit? TCP and IP are two different protocols. Each one works at a different layer of the OSI model. So TCP being a transport layer or transport protocol, sits at the transport layer of the OSI model, and then IP sits at the network layer, which is layer 3. I don't know why they wanted to do it like this. Maybe they want to throw this out at you to confuse you early on, but you really should have looked at the OSI model first, and then came to this slide where we talked about TCP/IP and where it falls into it. But I think they wanted you to know about the two different models. There is a TCP/IP model as well as an OSI model, but typically we would talk about the OSI first, and then we'd bring up TCP/IP model. I don't like the way they did that. Should have a slash in there. TCP/IP model, and afterwards. But here's the OSI model. So the OSI layered model is a logical and physical way of that people use for engineering. And here we go. Engineers use in device and program creation. It's a set of rules, a set of ways we do things. And me coming from a large network background, I would see myself really worrying about this the most, right? So when we're Network Plus learning right now, we're learning about Network Plus and how to be network engineers and or just learning about how networks work so we can be better at whatever our IT jobs are later on. We wanted to learn about this stuff right here. So we want to learn about the physical layer, data link, network, and transport. Those are important for us to learn about how things go across the network, right? Then we could talk more about the application layer. The application layer is the programs that we use that use these different layers and go up and down through the model. Presentation and session, I really never talk about in my day-to-day work. Typically, you're only talking about these four as a package and application, but we will speak about presentation and session and what they are for sure. All right, so some more about the OSI layered model. The application layer, applications can be either locally installed and run, or they're network aware, such as HTTP, web browsers, FTP, email, DNS, things like that. Christopher, I'm going to go ahead and mute you real quick here, and you can unmute yourself if you need to. You can use the chat function if you had to talk to me for anything, though. All right, so let's see, different layers. All right, so different layers perform different functions. So I was showing you earlier how we separated this section down here, and this is the section I like to think about whenever I'm talking about networking, right? Is this stuff right down here. So different layers perform different functions, right? When we say no worries, I absolutely understand, and we recorded the session, so you can go ahead and hit back on it after I post it. Transport layer, network layer, data link layer, physical layer. Everybody likes to call, like when we're talking about networking and people like to just like call everything packets, right? Well, they're not, right? So packets are only when they're related to the network layer. When we say that we're sending a packet over here to this guy and we're sending a packet to this guy, we're talking about network layer communications, right? So IP addressing and stuff like that. But when we're at different layers, we have different protocol PDUs right here. We have different types of PDUs that we use to call those PDUs, and when we're doing that at the transport layer, it's segments. When we're doing data link or Ethernet type layer, it's frames. And then when we're doing physical and we're talking about the network cards and the wire and the zeros and ones, that's the bits right here. So, all right, so physical layer. So physical layer talks about how bits are represented on the medium. That's the 0 and 1s. Wiring standards for connectors and jacks. Physical topologies. Synchronizing the bits. Bandwidth usage. Multiplexing strategies. They're all located on the physical layer. This is an example of current state modulation. And it shows voltage changes when it's off of 0. So when you're talking about going up with positive voltage, you go up with this in this direction right here, and when you go into negative voltage, you'd go down there. But if it's sitting at neutral or 0, they would be here. That's when we're talking about things on the wire. When we go into transition modulation, there's a smoother transition between those 0s and 1s, and you could see that happening here. These are new slides here, so I'd like to look at why they put it into this section right here. They must be going to a heavy physical layer discussion coming up here, so we're gonna visit it together. As those of you who are late, we talked about the new curriculum has been changed as of last semester. The 7th edition is being phased out, and they're going to the 8th edition, and that's why we're going to have a lot more stuff to go over in these 8 or 9 weeks that we're going to be here. All right, so signals flow from the network interface card into a transition medium, and those transition mediums could be different types of media. It could be a Ethernet cable or many different kinds of cables. It could be fiber, other stuff. In this connector, though, we're looking at an Ethernet cable. So in this connector, the transmission signals flow outbound on pins 1 and 3 and are received on pins 2 and 6. So because of that information right here, I know that this is Ethernet. So the pin out right here, this is 1 and this is 8. So they're trying to say that pins 1 and 3 are receiving pins, 1 and 3, and then I'm sorry, pins 1 and 3 are outbound or transmit pins, and then 2 and 6 are, nope, missed it. It's actually right there. Are the receiving pins, and we'll get into that more when we talk about it. But it's trying to show you the signal flow. That's what this is all about right now, and showing you that the bits go the bits go out on 1 and 3 when they come in on 2 and 6, and that's the physical layer 1 communications that happens at the when we're talking with Ethernet. With other wires and media, it's going to be different. So now it's saying we're going into we're discussing the path here. So now these signals have now been stored as data patterns in the header fields, right? The data link layer is mostly concerned with point-to-point connections, right? So this is now we're talking about data link. All right, so at the data link layer, we're going to talk about MACs, media access control, and LLC, less so much a logical link control, I believe. When we think about data link layer nowadays, we mostly are thinking about MAC addresses, physical addressing, logical topologies, method of transmitting on the media as the MAC addresses. LLC is as well connection services and synchronizing transmissions. So now the and you know what, I want to go back right here. I'm going to come back to this slide. This is 13. Talk about this right here quick. No, right here. When we talk about packets going through the OSI layer, I prefer that if they showed it to you this way first, to show you that when we say an application is being communicated through OSI layer, we could talk about things like HTTP, right? So HTTP. So at this application layer, we have a web browser, and we're looking for a website. So what's happening is that this information request is going through this OSI model, through the application layer. We made the request. Through the transport layer, we're making a TCP request, then an IP request. Then it goes on to the actual the link layer, the MAC address layer, data link layer, and it goes and gets to local network, and then it gets out to the physical network card, right? So that physical network card then communicates that out onto a wire, and that's could be that Ethernet cable. And then what happens is we go out and we go and get to wherever we need to get to, this new computer over here, let's say, that has the web server information, and it goes all through this OSI layer again on the other side. So I wish they'd show that earlier on, and I could do that too myself, but was it 18, 13? 13. All right. So we're going back up through the OSI model, like I was just explaining. So so network is the network layer is going to give you logical addressing. This is where your IP addressing is going to stay, right here at this layer. Switching can happen at the network layer. Switching also happens at the data link layer. It depends on what type of switching. Route discovery and selection. So route discovery and selection is choosing the best path to get to where you need to get to. Connection services, monitoring and bandwidth usage is going to be at the network layer. Multiplexing strategies are going to be at the network layer. Additional addressing information is added that enables a machine to connect to remote networks beyond its local area. Okay, and that's at the network layer. And at the transport layer. So at the transport layer, data is prepared for transport by repackaging each group of 1,500 bits into a segment with header fields. All right, so transport is going to do your TCP and UDP protocols, windowing, which is going to involve your 1,500 bits that you're using, buffering, getting the segments, because we're at transport, ready to transport to the next layer or the next location that it's going to. We're going to use buffering for that, right? So that's at the transport layer. All right, so then we go into this windowing concept. All right, so I was just talking about windowing. I mentioned that in the transport layer and in the 1,500 bytes. So the number of bytes sent is negotiated by the sender and receiver based on bandwidth and reliability, is what it says over here, right? So when we're negotiating window size, we can do that with the sender and the receiver. They can negotiate. So we get a segment 1, and then segment segment 1 does an ACK on that, and then we go. We send a different window size, and we say segment 2 and 3 we're sending now, and the receiver says, cool, that's good, I'm good with that, we're good, maybe you can bump it up a little bit. And then we go to window size 4, and he sends out 4, 5, 6, and 7. So he's sending out 4 different segments, right? And the receiver says, yep, I'm still good bandwidth-wise, that's fine, right? And during that process, we can keep negotiating based on my bandwidth available. All right, so session layer. Session layer is the first layer to initiate contact with a remote machine. It sets up sessions, maintains the sessions, tear down the sessions, right? So that's at the session layer. Session layer uses the transport layer for initiating the data session and setting up the three-way handshake previous to sending payload data. That's done at the session layer. And I like how it says session layer uses the transport layer. Okay, I'm not going to go any further than that, because really each of these layers are kind of hand in hand with each other, right? They have a little bit to do with each other because each one's passing on information to the other. Let's keep that in mind. So next we go and we look at the presentation layer, and a presentation layer is going to do things like, these are important, but not so much to me sometimes when I'm talking about networking, but these are important. Encryption and data formatting, they're all done at the presentation layer. So the presentation presents the data to the application layer as a unified file formatted to the needs of the network application. So again, it takes care of formatting and encryption before it gets to the application layer, right? So the application layer now, we'll go ahead and look at that. So application layer provides application services and service advertisements. Network-aware applications do not use locally stored data. They transmit and receive payload. You know, I have to say, they just produced this new material, and this is how somebody QA'd this and said, yeah, this looks good. I can't understand it sometimes. But network-aware applications do not use locally stored data. They transmit and receive payload data via port numbers. And we'll talk about port numbers. Port numbers sit at transport. All right, so data encapsulation in the OSI model. So sender creates data starting with the application layer, and then the receiver unveils the data starting with the physical layers. This is something I talked about earlier about the path the data takes, right? So they got to it, but they got to it later. I was too impatient. So so as application data moves down the stack, it is encapsulated with protocol field metadata. All right. So it goes down through the stack, hopping away, and then the physical layer gets on the wire and comes over to here. So bits arrive and headers are de-encapsulated until what is left is the original data. So it decapsulates this physical layer and passes it on to the data link layer saying, hey, I don't know what this stuff is, you do. Data link layer says, yep, I know that. Let me take my stuff out of there and send it up to here. Network layer says, okay, I got the IP address information and the header from that. I'm good with that. Let me take the transport segment and throw that up here. All right, so transport layer says, okay, we got the protocols, we got the ports, we've got everything I need. I'm going to go ahead and take that information, but I'm going to go ahead and send this on to the next layer. Session layer, go ahead and get that information, creates the session, the handshakes, things like that. And hands it off to presentation. Presentation layer says, okay, cool. I got the encryption information about the data. The data is encrypted. Let me decrypt it. All right, cool. Let me send it off to application layer. Application layer looks at the banking application now and says, okay, cool, we're logged in. Here you go, and presents it to the user. Again, this is the way it works for every single segment, packet, frame, and bit that gets sent across a network. All right, moving on to, again, now this would have been, I don't know why they mentioned it so early on in the presentation, but here's the TCP/IP stack again now. So when we as network engineers, we do a lot of thinking about the TCP/IP stack, and we like to say, hey, all this stuff right here, we don't care so much about it. We're just going to call it application stuff, all right? And this stuff right here, this data link, this physical and data link layer and MAC addresses and things like that. Yeah, we're just going to call that network interface stuff. But in the network world, we're concerned with these two. We're concerned with IP addresses. We're concerned with routing. We're concerned with those communication ports and segments and ports and protocols and things like that. We're worried about these two right here. So, so both are layered models, but the TCP/IP is considered to be under the umbrella of the OSI model. All right, so we're going to go into a couple things here. I'm not going to go through too much, but this is it's breaking down metadata header fields that are available in the network layer, and I think we're going to talk about the transport layer too. So in here, you're going to see version information for so what version is it? Is it IPv4? Is it IPv6? That'll be in here. The IPv6 one, we're going to look at those. We're going to look at those headers different, probably in week 2 or 3. They're a little bit differently. How big the header is, what service types it is, how big the total length is of it. All this data is going to be available in here, and it's going to be packaged up to be available to the network layer, and then packaged up and sent into the data link layer. And the data link layer is going to put on the its frame information and package all this into it, right? So all this information is available. You can go ahead and read more about that in the chapter, but we're not going to go too far into that right now. And then the transport layer has TCP metadata header fields, right? So here we have IP metadata fields. Here's TCP metadata fields because it's transport. So in here, we're going to have different fields available right here. So we're going to have source ports. We're going to have destination ports. If you don't know what a port is, you're going to learn about it very quickly. But it's an additional number that references the application that's being used. What do I mean by the application? That could be pings. It could be DNS. It could be network time protocol. It could be all kinds of different ports. There's thousands of ports, right? So we're gonna talk about ports. So sequence numbers are available in transport layer. Sequence number is where the packet lies in how it should be arriving, right? So sequence number 1 versus sequence number 2, 3, 4, 5. If I only have 4 and 5 and we don't have 1, 2, 3, we're not going to understand all the data that's coming at us, so we're missing some data. Acknowledgement numbers, checksum to make sure the data is good. Window information we talked about, how big packets are being sent. I'm sorry, this is segments. So how big the segments are being set, the window sizing, how many segments they can take, and we talk about that in this metadata field. And then TCP/IP TCP options are available, and they're only optional here. So transport layer has additional for UDP. So UDP is user datagram protocol, and in here we have a lot less information. Okay, you see now, you look at here, this is a TCP metadata header, lots of information. Metadata fields for UDP, we have source port, destination port, length, checksum. UDP provides a faster but less reliable method of delivery. The app developer makes the choice of UDP versus TCP. What would be a reason that we want to use a faster but less reliable method of delivery? And or what would be an example of something that we would be using? What application would we be using that uses this faster UDP protocol instead of TCP, which needs to have handshakes and acknowledgments, where UDP doesn't need to have handshakes or acknowledgments. It just sends it and that's it. Sure, online gaming. Well, Jeremy, maybe not transferring data, because we want to, it depends on the data, is really. So transferring data, what data is it, right? So yes and no. So what data is it, right? So how about a phone call? How about a phone call, right? UDP used for phone call. Live web stream. Web stream is good. Like how about Netflix? You know, you're streaming a movie, all right? Netflix doesn't need to know from you that you're receiving that movie. It could care less, right? It just wants to make sure you get it, and the fastest way possible. So UDP is a great way to do that, right? Doesn't require acknowledgments. The checksum is checking that the data is good. It hasn't been modified or messed with in transit. The checksums are good for that. We'll talk more about checksums. Of course. All right. So use of protocol metadata fields in a TCP/IP example. We got a client over here, and then we got a web server over here. And let's see what it says first. The source and destination addresses and ports are examples of data that could be in the fields you saw on the previous slides. Okay, thanks. All right, so use of protocol metadata fields in a TCP/IP example. We got some, all right, so we're doing a source IP address. We're doing the source port, the destination IP address, and the destination port. So we got port information, we have IP information. So, you know, destinations. So we have multiple metadata fields that are being used, right? And then when that communication request is made to port 80, so this is a service port. This is an application that we're looking for data on. And what are we doing? Port 80 is web. All right, so HTTP is port 80. So when we see this, we know we're looking at a request for web something, HTTP something, right? So maybe a website. And the web server over here at this IP address, which matches this destination, says, all right, I've got your data. I'm going to go ahead and send it back to you. All right, now the source becomes something different. The source address becomes that IP address. The source port is this source port of 80 from the web server. The destination, we're going over here to 10.1.1.1. The destination port, 1248, the same one that you came in on. Okay, this is a dynamic port. Okay, this isn't set to any specific application. This is just an arbitrary port that this client said, contact me back on this one, so I know it's for me. That's all that is. Port number assignments. We're going to talk about port numbers. Cool. All right, so we have dynamic and private ports. We have user ports, and we have system ports. These are port types, right? These common names for these types of ports is ephemeral ports, registered ports, and well-known ports. Okay, so these well-known ports are the ones that we're going to be talking about. A lot of the applications that we're going to be using. Okay, you're going to probably probably know about a lot of them, right? There's some of them I still mix up, but there's a lot of them, like port 22, I think, is secure FTP, or SSH it might be. 23, I think, is Telnet. 53 is DNS, I believe. 121 might be NTP. I can't remember them all, but you're going to want to, you know who's your friend for that is Google. So if you need to quickly know, hey, what TCP port 53 is, you can just Google it and it'll tell you. But you're going to be, as a network engineer, you're going to be dealing with ports a lot. These register ports or user ports are the 1024 to this 49,151 range. These are user ports. These are just ports that are used to communicate back to those users. They're not registered to any specific application at the time. And then also that falls for the dynamic ports as well, but they're never assigned. So let's take a look at protocols and port numbers. Let's see how many I got right. Telnet I got right. DNS I got right. Did I say 21? I said 22, secure. I didn't mention these two. So here's some well-known ports right here. So application layer protocol. This is the category of the application layer protocol. It's Telnet, SMTP, FTP, DNS, and these are the associated destination port numbers for those. And then where they fall in the transport layer protocols, right? Then we have, I'm sorry, those fall under TCP. And what that means is that when we're communicating with Telnet, SMTP, FTP, or DNS, we are using TCP, Transport Control Protocol, okay? And we are expecting communications back. We're expecting acknowledgments. We're expecting a handshake. We need this to properly communicate using these protocols, right? When we talk about these protocols right here, like TFTP and DNS, well, you notice that DNS is actually in both of them? Well, yes, because you want to request the DNS, but you're waiting for the response back. When the response comes back, it's going to use UDP because they are not going to talk back to you and check to make sure you got their information. You got to ask though to get acknowledgement with 53, and we don't need to go too much into that. But TFTP is Trivial File Transport Protocol. Sorry, that's a mouthful. You'll notice that it's got a lot. Let me get this eraser out here. You'll notice that TFTP looks a lot like FTP. So this is File Transport Protocol. This is Trivial File Transport Protocol. This one requires handshakes and TCP. This one is slim and quicker and doesn't require acknowledgments, but you could lose packets if the connection's not good and may have to redo the transport again. Why would anyone want to do that? Well, sometimes bandwidth is limited, or sometimes the application just doesn't support it for whatever reason. So we'd have to use TFTP. You're going to see this a lot in routers, switches, appliance devices, things like that are going to use TFTP, whereas applications on desktops that are using things like that are required, like important data transfers, are going to use FTP or secure FTP even, because they want to make sure that the data gets there. All right, moving on. So what does a finished PDU look like, right? So how would you plan to build the International Space Station in space? You can't send it all at once, so you build it on Earth, disassemble it, and send the parts and reassemble. Each piece gets an information label that provides insight on how to handle and reassemble the pieces in the right order. Pieces get boxed into a payload that will fit on one rocket. They arrive, unpackaged, and reassembled using the label information. The finished product in space looks like it did before it left Earth. The label information is like the header fields for a PDU. They tell the receiving computer how to take that payload and reassemble it for the intended application. So again, we're going from, we're looking at this now horizontal instead of vertical, but frame to packets, packets to segments, segments to data, data to the trailer, going up the OSI layer. So with frame headers, we go with IP headers, we go with TCP headers. The payload gets sent over and to the application, and we got a frame check sequence. All right. So I want to say that this is I've taught this class a few times in the past with the version 7, and it looks like they're doing is they're chopping it up more into more chapters, but the data, so Network Plus doesn't change. too much. Things come as new technologies come, and older technologies get phased out. But and I welcome that, because we were last time I taught this, we were still teaching about stuff from the 1980s and 1990s that I was implementing back when I was a lad, and it's really hasn't been used in 20 something years, 25 years maybe. So it's good to see that they're updating and get rid of some of that stuff. Maybe that's what's happening, but it looks like they're shortening chapters. So this is what are we at now? We're at 656. So chapter 1 is done. All right. So end of chapter thought question. Consider the difference between UDP and TCP. Feel free to think about this or post your answers and discuss it with me here. But we do this quickly because we want to jump into the next one. So consider the difference between UDP and TCP. If you were a developer creating an online game that relies on quick response times, which protocol would you pick and why? So I think I think I beat that dead horse pretty well of what we need to do if we wanted to do quick response times, right? And which protocol would be used for that, and that's going to be UDP, right? We want to use UDP because yeah, it's quick and doesn't require that response time, right? And this is a lot of games, online games, Xbox games, PlayStation, whatever you're playing around there. They use a lot of this because they don't want to have communications back and forth with you. Now there may be TCP communications that happen with you to see if you're still there, to make sure that you're on the network and still, and to drop you off the network if you lose connection, so you have a bad internet connection or something like that. They notice you're gone. So some application may be using TCP, but the communications back and forth between your client on your Xbox console or your computer game that you're playing, that's going to be using UDP to get that information to you quickly, because it's communicating with a lot of, especially in the online game with multiplayers and stuff like that. It needs to get that communication in and out quickly. So UDP is what's going to be used. Absolutely. Okay, cool. Any questions? All right, let's go ahead and give it 5 minutes. We're going to take a 5-minute break real quick. Do your bios or whatever you need to do, and we're going to get chapter 2 started and done, I think. So go ahead and take your 5-minute break. All right. We are ready to go right into networking topologies. So I think what I'm going to do is I'm going to go ahead and discuss this chapter here. And then what I'm going to do is I'm going to post up all the slides into one big package and throw them up on Canvas, so they're available for people to review. And I'm going to send another email out to the UCertify guys again and say, where is my codes? And then I have the takeaway of where's the hard copy for this book, and then PowerPoint slides and UCertify stuff. Yeah, no, of course. We're adults. You gotta do what you gotta do, absolutely. And don't worry, this will be recorded, so you can always come back and review it. This is a very self-paced course, and I'm here for you. So you contact me if you have any questions about it. Sure. All right, let's get this one done, and I think we'll come in a little bit earlier than 8 o'clock anyway. I think we'll be probably around 7:50 if this goes right. And I'll let you guys go a few minutes early, and then I'll get those tasks I promised you guys answers for, and I'll post them up in announcements. All right, so let's get this. We'll see how it goes. All right, so now we're on networking topologies and types. All right, so networks, defining a network. So networks are defined by geography, topology, and location of resources. So what does that mean? So let's go ahead and see what they have questions for here. So what is the purpose of a network? These are, so I'm not asking these questions to anybody specifically. So these are questions we're going to answer during this PowerPoint slides here. So what is the purpose of a network? What are some examples of network components? How are networks defined by geography, and how are networks defined by topology? And then finally, how are networks defined by resource location? We're going to look at all that stuff right here. So what are some examples of how you use networks every day, right? And this is again is a rhetorical question-ish, but we're going to go ahead and look at some answers on this right now. I'm trying to pull the screen down a little bit. Here we go. So what are some examples of how you use networks every day? I can answer this 1,000 different ways, but this is what I do for a living, and I'm a network guy, right? So one of them is going to be file sharing, right? So you're going to probably be having file shares available for work purposes. Um, um, I have Google Drive, I have Dropbox accounts, and I have OneDrive accounts as well. So I'm using a network to put those files up there every day. I'm in and out of my files, right? So that's something I'm going to be using. Video chat, Skype. I love how Skype's still in this, and they just created a new version, right? I mean, does anybody, you know what? There might still be somebody using Skype for business or something like that. But nowadays we're using what? We're using Zoom. We're using what we're using today right here. We're using WebEx, things like that. But yes, video chats, right? So every day I'm on a video chat. Yeah, Google Meetings, right? What's another one? Teams. Microsoft Teams is the one that everybody's going to be using real soon. You may not like it, or you may like it, right? But the reason why Microsoft Teams is going to become the big winner in this battle of video chat battles is, can anybody guess why this is Microsoft Teams is going to be the big one? Right there. That's it. It's money. So in your you know, and these are not going to go away. Zoom's not going to go away. Google Meet's not going to go away. None of those things. Security, yeah, Ali, that's a good point. Is security? Yes. There's a lot of reasons why each one is secure. All of them are pretty much using encryption, especially Microsoft Teams. I'm doing a lot of work for government agencies right now, specific government agencies, and they use Teams for their stuff. Yep, you can. Yep, absolutely. You can join Zoom meetings without an account. But the reason why this guy is going to do so well is because of money, right? So the reason why is because Zoom accounts more than 45 minutes. So companies want to have meetings that are more than 45 minutes. So you got to have a registered account that gets paid for. WebEx, the WebEx where I'm using right now, my company pays for, right? So it's an account that gets paid for on a monthly fee, right? So that's an extra amount of money. So they have Zoom accounts at my company, they have WebEx accounts at my company, and they have Microsoft Teams. But here's the thing. Teams is going to be there anyway because Microsoft's throwing it in there with your Office 365, right? So everybody's getting this Office 365 at their businesses right now, right? They get it because they have access to all the Office products, Microsoft Word, Microsoft Excel, Microsoft blah, 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 whatever. They get Microsoft Teams with it. They get Outlook with it. All that stuff is included with it. Teams does a pretty good job at also being a file sharing or storage, but you can also do more to it with it too. With the actual Teams module in there, you can do scheduling, task lists. There's plugins for it. If you haven't used Teams, it's really pretty powerful. And then voice calls, you can assign a direct inward dial, a DID. So you can actually get a real phone number assigned to your Teams account so people can call you from there. Microsoft releasing it, and now I work in my real job. I work in the contact center industry with workforce optimization, people calling contact centers and stuff like that. And Microsoft Teams is now trying to do a contact center, which is going to be tough because it's a tough business to get into. So, but if you got a client that's already doing all this stuff, and now you throw the ability to do a contact center on it, then you might show value to some companies, right? So Microsoft Teams, believe it or not, I think is going to become bigger and bigger because you're already spending money on it. Why would you want to spend money on something else? So look for that. Let me know in 5 years if I was right. So what other examples? Web surfing. Absolutely. Whenever I'm done with a meeting and I got a break, yeah. Whenever I'm done working, I got a break. I go looking at Amazon for something to buy, or just need a break. I'll look at something else because I'm shaking my head at the meeting I was just on, or something like that. So web surfing, instant messaging. That's your Teams. Yeah, is Teams pre-installed on 11 now? Is that what it is? Wow. So yeah, it's probably what do I call it, like a trial thing. They want to get you in there because they want you to buy it, right? They want you to subscribe. So, but it might be linked to your Microsoft account, depending on. I know they want you to log into your Windows boxes with your Microsoft account these days, so you might have a freebie Teams account linked to that anyway. Sure. So instant messaging, again, instant messaging is your Teams and your other applications. So instant messaging is included with Teams, but you also have the ability to do, video and all kinds of other stuff too. Social media, whenever I want to blow some time, I go to, I like how Vine's still here. But people are screwing around with Facebook, Twitter, and LinkedIn, and nowadays it's TikToks and stuff like that, right? I said to myself years ago, I would never get into that TikTok stuff, and somebody showed me something, and I swiped like 3 or 4 times, and now whenever I'm just sitting around, I'm just swiping TikToks because it's just a great waste of time if you're not doing anything else. So. Voice over IP, we're doing that constantly. Right now, we're technically doing voice over IP right now with this communications. But voice over IP is your phones, is your soft phones, is your Google Voice. You can do voice over IP. Believe it or not, your cell phones nowadays, a lot of the stuff that you're doing on those cell phones is voice over IP as well. Which of these require you to be on a different network than the one you normally connect to, right? A lot of them. Almost all of them. But then again, some don't, right? So you could do web surfing if you have local intranet. So you can do video chat with people on your network. You can do file sharing between computers on your network, but you can also do them off network. They use this 80-20 number, and we're not. This is probably outside of this course, but the 80-20 number used to be 20-80, right? And these are percents, right? So 80-20 is now you do 80% of your traffic off network and only 20% on network, right? Where it used to be the other way around, where you do 20% off network and 80% on network. That was 20 years ago. Sorry, what was I just missed it, Christopher? Sorry, what was not VPNs? One of these things should be not. What are some examples of how using networks? VPNs, sure, absolutely. I'd say VPNs is on there too, and we'll talk about VPNs in this course too. We have a whole good chapter on that as well. All right, so let's get cracking here. I spent a lot of time on that. All right, icons representing actual equipment. So we have routers over here. This is a switch. This is a hub. This is a client PC, and these are servers. And that's all this is just representation of these icons that we're going to use when we talk about networking components. These are them. Especially look at the difference between a hub and a switch, and we're going to discuss what the difference is. But a hub only has the one single line back and forth, where the switch has multiple lines going back and forth, and we'll discuss why that happens too. So network components. Connect the components together with some media and you have a network, right? So media, we're going to talk about defining that as well, but it says connect them with media, and that's just the wire that we connect them together, or the frame relay or WAN link, some sort of communications, or the Ethernet cable, or the RJ11 cable, or however we're communicating, right? That's the media they're talking about right there, the wire that connects each of these together. Networks defined by geography. So geography in this sense means how close the components are to each other. All right, so let's talk about the types of networks, right? Personal area networking. All right, we're going to talk about personal area networking. I think we have a slide for each of these, so I'm not going to go ahead into it too much. We're going to look at each slide. So personal area networking, local area networking, campus area networking, metropolitan area networking, wireless LANs, storage area networks, and wide area networking. All right, so personal area networks. All right, so what scale does this operate at? This is the human. This is the geography of the human scale right here, right? So I've got, I can't believe this is on here. These are those the Google glasses or something like that? That's a big flop. But yeah, those are on here. You got an Apple Watch. You've got these Fitbit, Nike type things over here, which nowadays you just screw, say I don't want that Fitbit type stuff. I'm just going to use my Apple Watch. It does everything nowadays. Apple's closing out that these guys aren't going to be needed anymore. I don't know what this is. A shoe with lights on it. I don't know whether that's a personal area network. And I have no idea what this is, but whatever. We'll just go ahead and look at. We'll move on here. But they're talking about the distance for personal area network is a few meters away. You can use a wired USB. You can use wireless Bluetooth. These kind of components are things like PCs, headphones, keyboards, smartphones, so on. I'm surprised they don't have a BlackBerry here. I can't believe what's this all about right here. I don't know. Local area networks. So local area networks scale differently. So they scale a little bit larger. So they're a room or a building, right? And this is a network that is local, or generally in that one little building area. Think your office building that you work in, but just that one building, right? Not the building next door, right? So local area networks, right? Distance is usually 100 meters or less. Your media for this is, so your media is your communications wire, your method of communication. So media can be a wire, or it can also be wireless. So in this case, the air is your media. You're communicating over the air using wireless. Components include things like PCs. We got routers. We got switches. We have some servers in here, file servers, print servers, other things like that. Printers. Is there a printer on here? No, there's not, but printers are included with there. Wireless access points. These are all things on a local area networking. Wide area networks. Wide area networks include the scale of a state, a country, the world. Okay, so the scale of a wide area network can get very large. Distance is a few miles to thousands of miles. Media can be wired, or I don't know why they do this. It could be wireless, I guess. But in the case of global or wide area networks, I wouldn't say microwave, but I might go ahead and go maybe LTE. Okay, your cell phones. Those are wide area networks now. You're on a wide area network every day because you're using your cell phone to connect to a tower using LTE or 5G or whatever it is nowadays, and you're on a network using that, right? Components include routers, switches, satellites, and so on. Campus area networking. Your scale is a cluster of buildings. And this is like think of when they say campus, I think of colleges anyway. So right, think of your FSCJ college campus, right? So it's a cluster of different buildings. Distance is usually a mile or less. You got fiber, coax, maybe not coax so much anymore. Fiber's getting so cheap. It's just the way to go when you're going these long distances, right? So fiber more so. I know I crossed it out, but for the purposes of learning, keep in mind coax is involved as well. Wireless is 802.11 and microwave. So these are options as well. There's also other types of wireless, like a direct connection. So like you can have a dish over here and a dish over here, and it's like a point-to-point link between buildings. That's available as well. They're really slow. You're better off using wireless bridging or fiber connections between the buildings. Components that are involved here are going to be routers and switches for sure. Wireless bridges, like I was just talking about, that point to point, that would be a wireless bridge, and so on. MANs or metropolitan area networks are the scale of a city, usually a few miles or less. They can use fiber and coax. They can also use wireless, regular wireless, maybe 802.11 as well, but you can use microwave, I guess, as well. But you'd have wireless access points with a fiber backbone or Ethernet backbones that connect to the infrastructure. Routers, switches, wireless bridges, and so on. I was in Minneapolis going back years ago for training, and it intrigued me. It was probably back in 2014 that I'd walk down the street and it would advertise the city's sponsored wireless access points. So kind of the way that Comcast steals everybody's not Comcast, yeah, Comcast or Xfinity. Sorry. So Xfinity, if you notice that if you have Xfinity right now, you may notice that there's a Xfinity Wi-Fi that's being broadcast around your area as well. It's probably your Xfinity that's doing it. Xfinity takes a little bit of your bandwidth for their own and uses that to create this wide area network that others can use if they're a customer of Xfinity. So this metropolitan area network in Minneapolis had this network available all around the city where you just walked around and you'd have, I forgot what the name of the broadcast was, but it was an SSID like, Minneapolis City or something like that. And you just, public Wi-Fi, and you just connect to it, and you can connect to Wi-Fi wherever you are in the city. It's pretty cool. Networks defined by topology. So topology, in this sense, means how the components are connected to each other. Okay. It also can point to a specific technology being used. We're going to talk about these, but the bus is an older one that we're going to talk about, but it could be a logical or it could be a physical topology, as well as rings, stars, hub and spoke, full mesh, and a partial mesh. We're going to discuss. All right, so bus topology, number one. All right, so I am so old that I actually wired these networks way back when. These physical networks are a cable. This is actually a physical cable with a cap on the end here, terminators they're called. And then they'd have sections that branch off and go to a computer using a coaxial cable. Coaxial cable was a RJ Uh, 11, no, RJ, 52, 53. It was so long ago. But it was a thinner cable than you're used to coming from your cable TV. It's much thinner than that, and you'd just branch off here. And this would be called 10 base 2, 10 base 10, 10 base T, 10 base T, because of the T connectors. It was a single coax wire using the T connectors. Devices could send and receive data, but not at the same time, and the signals would bump into each other. And those are called, what this is called collisions. We're going to talk about collisions later on. And these signals would bump into each other and be corrupted, and then we'd have to wait for everybody to play fair and communicate on this wire together. This is no longer in use, is absolutely correct. Anybody that's using this is out of their skulls. But useful for understanding Ethernet networking. All right. So yes, 30 years ago. Was it 30 years ago? It was 30 years ago. We were still using this in some places, even though there was the technology we use today that was still available. People were just being slow about implementing it because it cost money. Technology today in companies is much more important than it was 30 years ago. IT and technology fell under a branch of the company, even in big enterprises, that were like the financial departments. So the CFO, the chief financial officer, would be in charge of IT. Nowadays, there's CIOs, where chief information officers, who are IT people. They're not business people per se, are in charge of these things. So there's more importance put on technology today. Obviously, I don't know the demographics of this class here. I don't know about young or old, if they remember what this was like, but back in the 90s and early 2000s, getting buy-in from your company to spend money on technology was pulling teeth, where nowadays there's plenty of budget, because now you're running into issues with cyber hacks and securities and fines and penalties and things like that, and lawsuits, because you're not doing things right. Well, now you have to, right? All right, so this is a ring or token topology. And in this topology here, what we would see is that, I'll talk briefly about it here. This is a MUX right here. This is a multi-user something. I can't remember what it's called, the acronym, but what it is it's basically a switch for a token ring network. And what it did was, all these computers have a network card on them, and the network card, if you want to Google it, you can look at it. But and I've actually installed these, but here's what it was right here. So this is a network card that actually plugged into the computer. All right. And this is the back of the network card. All right. And it had these two ports on the back of it. Google token ring network adapter, and you'll see what I'm talking about. And then on this, it would have two of them. So you see that's an in and an out. So the cable comes in, cable comes out. So it's a transmit and a receive, two different ports on there, and it's a cable wire that comes on there, and everybody was connected to each other. So this guy was connected to this guy, this guy was connected to this guy, this guy was connected to this guy, and they all got connected to this guy right here. This guy right here in the middle, he would be the communicator. So now I'm talking about it in two different senses here. So I'm talking about this, everybody's connected to everybody. In the original rings, that was a physical topology where everybody would be connected to everybody, right? Later on, when this technology became more advanced, we implemented the MUX, and everybody plugged into the MUX, their ins and outs, and the MUX would deal with the communications of this token. So let's talk about what happens here, right? So, all right, so what happens here is, come on, get my pen back. So you remember what we discussed over here with this bus topology here. Signals would bump into each other and be corrupted. In the token ring topology, that wouldn't happen. You weren't allowed to talk unless you had the token, okay? if you ever read or saw the movie Lord of the Rings, you weren't allowed to talk unless you had the conch. All right. So I got the conch, I'm talking. So this is the same thing. This is the token. This guy can communicate. He communicates because he has the token. When he's done talking, he passes it to this guy. This guy can communicate. This prevented collisions and was more efficient. This topology stopped in the 90s, though, because Ethernet became better. Star topology. In the star topology, we took this original hub. I'm sorry, this bus. We took this bus logical topology right here, and we made it a little more efficient. In this way, we had the wires all going to here, and this device right here is responsible for repeating the signal between the devices. If you remember, I told you remember what these devices are. This right here is not a switch, it's an Ethernet hub. And it uses something called CSMA, collision sense media avoidance with collision detection. Carrier sense, no, it's carrier sense media avoidance. No, it's not avoidance with collision detection, but it uses CD. We're going to talk about CA when we talk about wireless, but this is CD, collision detection. Typically, it would have a twisted pair wire set capable of simultaneously send and receive signals, right? So this is where we come with this twisted pair as we start talking more about Ethernet. This avoids some of the collisions that would have crippled a pure bus topology. Notice how it says pure? Because this is technically still a bus, but with a star physical topology, but a logical bus, because the bus is in here. This is the bus. It still has little computer ports on here, and they all communicate on the bus. And this is where we start distinguishing between logical and physical, and logical and physical topologies, right? Again, this is a star topology that is physically a star, but it's still logically a bus. So then we got a hub and spoke topology, and these icons are routers. Okay, these are all routers. Routers connected to other routers are forming WAN links. Routers connect Ethernet LANs together. New technicians often confuse this with a star topology. The use of a central router may seem like it is at the center of a star topology, but is called hub and spoke in reference to a wagon wheel, not because there's an Ethernet hub. Next, we're going to talk about the meshes, right? So we're going right into routing full meshes, right? So full mesh, using a full mesh means every router is connected. Oh, wow, that was a horrible underline right there. Sorry. Full mesh means every router is connected to every other router. That's what full mesh is, right? Mesh is not necessarily, full mesh is not necessarily only to be used when we talk about topologies with routers. This could be used with switching and other ways too of having a full mesh connection. But most of the time when we talk about a full mesh, we're talking about these routing topologies to make sure that every router has communication with every other router in case there's a break. So if this breaks, this guy can still get to this guy another way, right? This ensures that no one's link failure can bring down a network. This topology can make networks very expensive. Why? Because these leased lines are really expensive per month. So you have to pay monthly fees on having each of these lines. So if each of these guys you got to pay 3 lines for, it gets expensive. So people usually go to the next page and they'll use a partial mesh. And a partial mesh is similar to a full mesh because no one link failure can bring down any single part of the network. It's less expensive though because we're using less. All right, so this guy right here does not have a link to this guy, but he has link to the other 3 over here. All right, and this guy right here, he may have a link to all of them, but this guy over here does not have a link to all of them. And these 2 down here, they only have links to these over here. So why is it done this way? Well, we don't know, right? Geographically, this guy over here may be a small office that just needs to have 2 connections one as a backup, right? And these right here, this might be the big corporate office right here, and this might be the secondary corporate office over here. So they may want to have those big backup connections, and these guys communicate with them. But the more important part is we need 1, 2, 3, 4, 5, 6 in this partial mesh, whereas in this one we need a lot more. I'm not going to count them all, but probably about 10 different links in here. So we're saving monthly fees on that. All right, so now we're going to talk a little bit about client server and peer-to-peer. So networks defined by resource location. All right, so we'll talk about client server, and we'll talk about dedicated server devices, shared access, network printers, centralized and tight controlled administration. Then we'll talk about peer-to-peer, and then we'll talk about peer-to-peer file sharing between PCs, and then directly attached printers. We'll talk about the issues that those pose with scalability. And we note that most home networks are peer-to-peer when it comes to security, but they may be using some centralized client-server features. And these are called hybrid networks from an administration view. All right. All right. So client-server networks, client-server networks. We got a file server. And here, what do we got here? We got an icon that you're familiar with now, right? So this one is not the hub that we're used to. This is a switch. All right, so it's asking a question here. Are there 2 servers in this graphic? What do you think? I would probably say there's one right here. And I would say this right here is this is a server as well. Why? Because it's a network printer, and on this network printer is a built-in or it's an attached print server. And this print server basically allows these clients to send print jobs out there. Because it's not directly connected to any specific client, it is a print server most likely. And are there 2 servers in this graph? What do you think? You can see the file server. The network print server is also a server. It provides print services. Print server. There you go. Yes. No. File server is giving the printer a server from the switch. We don't know in this case, Christopher. So in this case, the file server could be acting as a print server for the printer. It's definitely possible. Back in the day, that used to be something, but nowadays, I've got a printer behind me sitting over here with a Wi-Fi connection, and it's got an IP address built into it with a network card on it. It's a print server, and it's standalone. But back in the day, you used to have a file server, and you used to have to attach printers to the file server for computers to print to that file server, but not anymore. Peer-to-peer networking. Each peer PC has resources to share or controls access to its local disk drive, folders, and files. The peer machine connected to the printer controls access to that device completely. It has to share for others to use it. So in this case, this is not a print server. This is a printer connected to this computer. This computer can share this printer for others to use in a peer-to-peer. Multi-protocol label switching. Oh, they went right into this, huh? All right. So MPLS is a technology that we use. It's an upgrade from the old frame relays. I don't know why this is being used right now, but they talk about it. I don't know why we're bringing this up right now. We're not talking about this in wide area networking, but cloud services use a combination of topologies and technologies. This type of hybrid topology is very common, and it's just showing that there's an ability to have this MPLS communications in this cloud right here. Again, MPLS stands for multi-protocol label switching, but this is a type of wide area networking. I want to come over here. I don't believe this belongs in this area. This doesn't belong here. We'll probably come back to it. But this is a wide area networking slide. Again, these are all new slides, so they probably created them at Pearson and didn't, and the QA person was fired or something. All right, so Again, network virtualization doesn't belong here. Network virtualization functions, virtual switches, virtual desktops don't belong here. I'm going to skip over this if you don't mind. This does not belong here. Digital subscriber lines. We could talk about DSL a little bit, I guess. Let's talk about these a little bit. I'm not going to talk about network virtualization right now. Satellite connections. Let's talk about that. Satellite connections. You got a. This is a type of wide area network that you can use. I would say this is something you want to be only using if you have to. Okay. Because the speed of satellite internet is excruciating. If you've ever dealt with dial-up connections, it's very similar to that. Although you can get a decent download speed, and decent, by decent I mean probably as much as 10 megabits. Typically, the sending back from your client, you can't transmit satellite. So your transmission would be through a telephone line using like a 56K modem or something like that, which is excruciating. So that's satellite connections. And where this is needed is it's going to be needed somewhere like, don't get mad at me if you're out in Utah, but somewhere in the middle of mountains and farms where there's no civilization and there's no internet and they barely have phones and stuff like that. This is the internet you're probably going to have, right? Because that's all that's available. You may take for granted that we have this gigabit fiber to our houses right now, but we have this because we're populated. We're in a populated area. But when there's an area that there's only one person per 20 miles, right? Then it doesn't make sense for the companies, the big companies, to put these big services out there. So they're not going to spend the money on it for that one guy who needs the internet over there. So that's something you got to think of. So satellite is something that you can use for that, but it's slow. You're going to do most of your 56K would be you requesting the web page, and your 10 meg would be your downloads, right? Stuff like that, maybe. DSL, digital subscriber lines, are still around today. It's a couple different connections that you'll have. You'll have multiple. It'll be two 56K lines, two 56K phone lines with an additional line for signaling. ADSL is asynchronous DSL is a common one that you'd see being used. I say asynchronous because its uploads and downloads are different. They got a DSLAM, which is a multiplexer, goes out to here. Verizon, Fios, DSL. I wanted to get that service once. You know, I have to look at that. Fios, I thought was fiber. I'm not sure exactly what that is, Christopher, but we don't have that here in my area. But it is fiber. Okay. I'm not sure why it's a DSL. If it's fiber, maybe they're just tagging it with cool taglines, but I don't think it's actually digital subscriber lines, because DSL is using a different type of technology. But I would look at that to see what it is. If Fios is fiber, it's probably not DSL, but I'm not sure. I don't know what it is exactly. But it has some information here. Limitations of DSL is causing providers to evolve into using fiber links. So this is going out the door. Last time I saw DSL was probably in early 2006, 2005. Yeah, I mean, it's fiber is so cheap. It's so easy. Seriously, Xfinity is going to need to, they're doing it too, but yeah, yeah. Everybody needs to keep up. And if you're a service provider that's providing high-speed internet and you're not providing fiber, you're going to be gone soon. I'm spending 60 bucks a month for 1,000 megabits and 1 gig, 60 bucks a month. I mean, I spent 60 bucks a month back in 1996 on 2 meg, right? So 2 meg cable, I spent 60 bucks a month on. So, yes, it is a deal. Just be sure to check back with AT&T or whoever your provider is every once in a while. Threaten to cancel, call back again, say I want the new deal, you'll get it. They're offering the gigabits at cheaper prices because the 2 gig and the 3 gig are becoming available. I think there's a 6 gig now, and if you need 6 gig, God bless you. Just because I do a lot of internet stuff. I do a lot of streaming. I do a lot of serving files and streams from my house, and 1 gig is fine for me. Cable modem is broadband. Here again, coax is being replaced by fiber. Again, I don't know if that's, well, you're still getting coax on your last mile, your connection to your house. But I believe, I don't know if Comcast is actually doing it yet with fiber to the house. I think it's fiber to their locations nearby, and then the last mile is coax still. But I haven't had Comcast in a while, so they may actually be doing fiber now. Yeah, so there you go. So it still has coax, and the coax can go at those high speeds for a little bit, but it can't go the distances that the fiber can. Plus, I don't think Comcast wants to sit there and throw fiber to everybody's house. They want to go the cheaper method, especially with cables that can coaxial cables cheap to fix and replace. Fiber cable requires a specialized technician with a torch and special tools to fix the fiber lines. They don't want that. Other networking topologies and technology on the Network Plus exam include leased lines. And I mentioned leased lines earlier, and leased lines are going to be your communications between multiple routers, right? So those lines that you saw earlier between these routers, these bolts, lightning bolts, these are going to be your leased lines that you'd see connected right here. And we'll talk more about what these are and their speeds when we get into the next chapters, I believe. Metro optical or Metro E are options as well. This just mean metro. There's a taggy line for or name for these metropolitan, these local city type ones that are available. But Metro Optical and Metro E are two different replacements for things like MPLS that are becoming up and coming for businesses to have really good fast connections between their sites. Instead of using the old leased lines, you'll go to these Metro E's and Metro Opticals. And then SD-WANs, which is software defined wired area networking. And this is something, take care. And this is something that we are seeing become more and more popular with these software defined networks. And I think we offer a class in software defined networking, if not a class that has a portion of it with SD-WAN involved with it. And then here we go, we're wrapping up. All right, so thought discussion question. Small peer-to-peer networks are easier and cheaper to administer than centrally administered domains. If the network size is growing, at what point does it make sense to switch to a central server? As an example, what about your residential environment? By the time the game consoles, TVs, Amazon Alexa printers, and Google devices are added in, your residential network could be quite a large number as well. What should your administration plan look like? All right, so these are things to think about, but with small peer-to-peer networks are easier and cheaper to manage. The network size is growing. At what point does it make sense to switch to a central server? I mean, there's no reason for anyone to have a peer-to-peer network anymore. Unless, except for home networks, maybe. But in the business world, I'm thinking there's no reason to have a peer-to-peer network in a business anymore. Because this, and I'm going to go ahead and throw the ideas out there and go ahead and type in if you want as well. But the reasons why you want to have a centralized domain is security. You also want to have a centralized domain for file storage and backup recovery, disaster recovery. So if you have a server that holds all that information, I mean, I even have that here in my house. If you have a server that holds all that information and you don't want to lose that information, you don't want people storing all that crap on their local computers and sharing it from computer to computer, because then what's your backup strategy and what's your security strategy? You should always be going to a centrally administered domain with backup recovery and security measures in your networks if you're a company. Absolutely. Even if you're a small company of 2 or 3 people, a small law office, whatever, you got to have your stuff backed up. That's my thought. That's my thought and my discussion. So you think about that. All right. We're at 7:52. I promised I came through. I got you guys to the summary. We talked about these, and we're going to talk more about these types of networks, but client server, peer-to-peer we talked about. We talked about hub, switch, and routers. We talked about medias and WAN links. We talked about geography, topology, and the administrative models, right? So cool. We got through it all. I'm gonna go ahead and stop this recording. If anybody has any questions,